same signal, but they are separate within certain distance. I mean, from the power cable, and then you will see this is the original one without any, with only one lamp. This is the 16 clamp constellation point. With certain modulation error and other things, it's no longer a single point, but still you can clearly see they can be successfully separated, and this is the spectrum. Usually it should be grid drop, but with the degradation introduced by the power cable, it's no longer flat anymore. But if you have straight lamps, like showing the configuration showing here, the spectrum is totally unrecognizable, and in the meantime, the constellation mapping is kind of blurred. Thanks to the powerful system design and also the error correction coding, we're still able to recover the video content without any problem. So this shows the worst case scenario. And the application could be like, for some cases like tunnel without hard signal, you can use this VLC because there is always lightning or illumination network and power cables, and then you can use that to realize communication. And also you can use that for to find your car if you park that on the ground. Also, like for the smart grid, sometimes it's electromagnetic signal sensitive or even prohibited, then you can use it. And for perhaps for the hospital, which is also RF signal sensitive. So I can see, this is something you can use for the subway. So from that, we can see there is a strong demand for using the VLC communications, only because of the advantages offered by the LED-based VLC technology. But we see that the current setup for the PLC system, it has certain disadvantages. So therefore, which motivates us to propose a new system. So here, just have a quick illustration on how this evolution of the network structure. The traditionally one, you will see that it is inside the house, you will have this power cable which provides electricity to each LED light, help to illuminate certain areas. But in the meantime, you can feed the information through the coaxial cable or other things. So you combine these two things together, you can provide certain coverage. And the disadvantage of this infrastructure is because the apartment or house or infrastructure is already there. So you have to have a new installation, which is quite complicated. And in the meantime, if each light illuminates certain area with different information, then you will see strong interference among each other. And also, if people need to move from one area, coverage area, under one LED to another one, you need a lot of switch off or switch over. And the second one, we call the combined PLC and VLC network. Basically, that one, you use the power cable to not only just provide electricity to illuminate the LED, but in the meantime, you send information to each LED. But you have to decode it and then modulate it to LED such that each area is covered by the different information to serve different users. So with this one, it's still complicated, even though you don't have to install the new, you don't need to do the new wiring, but in the meantime, you still see the problem of the switchover, you still see the problem of the interference. So we call this arrangement like the decode and forward mode, similarly like what we see in the wireless communication. Basically, you receive the information, you demodulate it, try to recover it from the errors and interference, make it clean, and then do the modulation again. And the third one is what we propose. We call the integration of the PLC and the VLC system. If we compare that in its counterpart in wireless communication, it's like amplified forward mode. So basically, you use the same power to deliver the same information to all the LED lamps connected to this same power cable. And in the meantime, basically each LED lamp will transmit the same information. Of course, perhaps with certain delay because of the length of the power cable. And in this case, in the terminology of our broadcasting, it forms a kind of so-called single frequency network, which means all the transmitter will transmit the similar, if not identical signal, almost at the same time, under the same frequency. So with that, basically we can enjoy the benefit of low cost and low complexity for the implementation and easy to build. And second is because of this large coverage, it avoids any anti-shadowing and interference problem. And the third one is it can provide you certain scalability and flexibility. If you want certain area being covered with one type of program and another area being covered by other programs, you can try to add more base stations. So it's kind of flexible and with good stability. This one, we have just proposed a frame structure of integrating both the PLC and VLC system. We haven't highlighted or we haven't explained the advantage of this structure in terms of the implementation. You can see that within a very small light, LED light, inside it, it's difficult to accommodate many, many hardware modules like the demodulator and also some power module to convert AC power into either the DC, like 5 or 12 volts. So basically, with our arrangement, you do minimum modification on the existing LED lamp, and in the meantime, it can provide certain good coverage. In order to make this thing work, we need to consider a couple of things. As I said, we're not trying to, we're expanding our idea, but in the meantime, we're kind of thinking or trying to stimulate more research work. One thing is to consider spectrum allocation. So here is the location of the power line communication. So basically, anything below 500 kilohertz is for the automatic meter reading, or we call the narrowband PLC system, which are familiar with each other. And anything beyond 2 megahertz is considered a broadband. I'm from the northern part of China, so it really humidity kills me. Thank you for turning on the AC. And also this is proposed arrangement for the PLC system. So basically we believe that anything beyond 2 megahertz can be a high-speed services, which is corresponding to the PLC system. And anything below 2 megahertz can be utilized to broadcast the ID information of each LED, which help to provide the location-based services in the future. And for the receiver, we can basically either use the so-called on-the-go program or use the existing CCD on the cellular phone to receive this information, ID information to help you to navigate for the navigation. And for high-speed, of course, right now, there is no chip available inside the cellular phone, so you have to use this on-the-go model. And this is a simple allocation, but you got to keep in mind that for the VLC, like people proposed yesterday, or I think one or two students had mentioned last time, that for the VLC or LED, you will have some dimmer, which help you to actually adjust the light intensity. That could jeopardize your ID broadcasting. So we need to carefully look into this spectrum allocation issue, making sure that different functionalities of the VLC system can be allocated the individual frequency such that no mutual interference will occur. And another thing is, if you're trying to maximize the system performance, you need to have better understanding on the channel, such that you can design the better coding moderating scheme and design the better system structure, or vice versa. So from this sense, you need to consider the channel model for the power line communication. We've done some work. We have done 7-day, 24 hours monitoring on the PLC channel. So we also try to model this channel using the well-established multipath or ACT model. So this is our measurement, both the noise and interference, similar like this. So it's really the attenuation increase with the increase of the frequency, while the noise intensity decreases with the increase of the frequency. And also, if you consider the VLC channel, you need to consider several things, both the time, frequency, wavelength, and the space property of the VLC system. And in the meantime, if we talk about space, we check the noise. The noise is no longer linear because of this light intensity and current conversion. And it's no longer Gaussian because you have Poisson noise, like people pointed out last time. And also it's no longer additive because of this light to current conversion. And also the status of the receiver will have a great impact on the system reception performance. So we need to have a better understanding of that. And also for the indoor, as I mentioned, you can automation pushing or like advertisement pushing to provide certain services to users. And another thing we'd like to mention is how to divide the channel approaching or capacity approaching coding and modulation scheme. So again, based on what we have developed in the broadcasting area, we have proposed this type of scheme. And also, in order to solve the problem of the OIPM, which is suffering from the high peak to average ratio, we propose so-called the active constellation expansion algorithm, try to lower the peak to average value, try to save the performance in order to make sure that it is in the medium range. And also for the field structure, basically we use the TDS OIPM technology. The beauty of that we have expanded already. And if we talk about this thing to be like two-way communication, so we are thinking that we will use a TDD type of structure. So basically, we use each time slot for each user to be able to access to the network, and each time slot will contain many OIPM signals, which including both the training sequence as well as the payload data. And that one, we're thinking, or we're investigating to see if with that arrangement, we can even deliver certain service or minimum data throughput during the daylight. You have to turn off the light. Actually, you're not turning off the light. You change the way you turn on the light and turn off the light quickly, like within 1% or 2% occupation cycle. And human body's eye won't be able to recognize the light is on, but in the meantime, you actually deliver the information within that short period to minimize, or to give you a minimized service for the location services. Okay. And also you need to consider the network structure because as we mentioned, with this single frequency network, still from one single frequency network to another one, you need to find appropriate algorithm or appropriate strategy for this handover. This could be both homogeneous or heterogeneous this network. So this is something we consider for this type of system. Some working are going on, something we just have very rough planning. We haven't conducted very detailed investigation in that. So that's why I'm kind of hoping with this brief introduction we can stimulate or attract more people to consider that, and then we can work together to get some fruitful results. Okay, as I mentioned, I'm not the information theory guy, but information theory is our best friend. So basically, when we design the coding modulation schemes, we take advantage of the latest developments from the information theory, like the network information theory. We use the so-called nonlinear superposition coding to allocate the resource or try to divide the services on bit level such that we can accommodate different users at the same time to maximize the system throughput. So here is the illustrative figure to show how this thing looks like. I will have a clear picture for that, but basically it gives you the idea showing that if this one is the time, for example, x-axis is time, vertical is the index of bit with each data symbol. You can allocate the whole data symbol to one user and another set to another user, or you can allocate certain bit of each data symbol to one user while the rest to the other user. We are using just two user case as a simple example. If later on you have many different services which has the different required signal to noise ratio threshold, you can somehow take advantage of this arrangement to maximize your data throughput. So I will try to expand that in details later on. Okay. So here is I'm trying to borrow a slide from Kusner 3 years ago. Basically, he used this slide to compare this theoretical bug and also the existing systems. You will see if you consider the trade-off between the implementation cost and also the performance, it's not very close. On the different signal to noise ratio, it's very close to the theoretical bug. So what we're supposed to do? So basically, we figure out that the traditional way is the point-to-multipoint or point-to-point transmission. It's still like a time division multiplexing or the frequency of total division multiplexing. called orthogonal multiple access scheme. So can we do it better? Can we like take advantage of this, again, like the network information theory, to support multi-user transmission instead of or in a non-orthogonal way? So this is something we see from the literature. And we basically have a very abstract channel model. It's the so-called broadcast channel model. So this is the base station. Assuming you have three different messages. M0 is the common message to both for these two users. And M1 and M2 are private users for each individual one. And you have two ways to allocate the resource to support this requirement. If you do the time sharing, for this sketch, you will see that if this is the capacity for channel 1, for user 1, for user 2, you will have this straight line. You can allocate the resource either to solely to user 1 or user 2, or you can have a combination. But if you allow, or if you are doing the innovative thinking to use a non-orthogonal method, or which we call superposition coding, this is one example of that. You can perhaps provide to get the capacity curve like this. So if you compare these two, you will see some capacity gain if you want to support both users simultaneously. How to do that? Before we continue to explain our idea for the BDM, we just give a very generic description on the superposition coding. So assuming we have, so this is the total algorithm space of the constellation point. So for the linear superposition coding, you can have this cluster, three clusters, just for argument's sake, to deliver the information if the user is under non-favorable conditions. And if the user is under the very favorable reception conditions, all those points inside this class can also be recognized. So therefore, it carries more information. So for the linear superposition coding, basically you need to find the appropriate power state ratio such that you can maximize your data throughput. And again, this is a better illustration of our BDM idea. So again, this is a symbol. Just assuming, because symbol is equivalent to time, you have, for example, you group 12 data symbols as a block, and then you just allocate certain bits, which is this shadow one to user 1 and the rest one to user 2. For each data symbol, you can either allocate to one user or allocate to two users. So with this arrangement, you take advantage of the unequal protection ratio of each individual bit after you do the constellation mapping, and you can deliver the information to end user with a better channel capacity. This is one example, which I believe would be clearly indicate how we can take advantage of this scheme. So this solid curve in black is the theoretical capacity. And for BDM, with our idea, you can see it's very close to this capacity ratio. And this is for the orthogonal division multiplexing coding without TDMA. And the other two are from the linear superposition coding. So you can see from this illustration, given certain signal-to-noise ratio difference between two users, we can design a code such that it can well approach the channel capacity at different service, different data throughput from different users, from these two users. So you can choose any other combination of two, and it's very close to the current capacity. Okay, so this is for the broadcasting channel. Another channel we call the multiple access channel. Basically, in this case, it is upping. So assuming you have two users, of course you have many. As long as these users have different service require signal-to-noise ratio. If they have certain difference, then you can assign different bits. Sorry, you can assign different powers to different users, and then you combine that. At the receive side, they can, the base station can receive the private information from both users. Okay, so this is the idea. So from this one, you can clearly see that it is a nature linear superposition coding. Right? In this case, you don't have the luxury to combine the information bits from two users together, because each user they only operate by their own. So therefore, they have their own coding moderation scheme, and then you combine them together with the appropriate power allocation, and then at the receive side, with this certain point, which we call the arm, you will see the same capacity, but for the other regions, basically the non-orthogonal or MAC, the proposed linear superposition coding can outperform this OMA or orthogonal multiple access. So you get multi-users, basically you can use the iterative way because you're now using the linear superposition coding. So at the receive side, you need to do cancellation. So you get the strong signal being decoded first, and then you try to subtract the impact of this strong code, and then to decode the second one. Again, if you have several users which have different signal-to-noise ratio threshold, you can do it one by one. But you will see that if you want to have many users, it's going to be kind of difficult. So that's pretty much shows the idea of our proposed EDM from both downlink using the broadcasting channel and uplink multiple access channel. So another is based on what we studied. So you can somehow, based on the signal-to-noise ratio and design code. So here you see this is the theoretical bound, this is the prime, this is AKS. And this is some result. We can clearly quantitatively know how far we are from the theoretical bound and how much degradation comes from each non-ideal scenario. So this is a very preliminary work for the so-called deep interleaved coding modulation with iterative decoding demodulation, which motivates us with the bit division multiplexing. And in summary, I'm just trying to see that there exists a major combination of the power line, power cable, and LED network. So basically, the illumination network and the power line communication network can be integrated for the communication purpose. And it's similar like the network cable carries connecting to the Wi-Fi. And the amplification and forward scheme, it provides us a very practical way to achieve this purpose with very low, or I would say minimum implementation cost, and can avoid the shattering and the frequency handover problem in the future if the user is under availability. And still, as I said, I'm just trying to stimulate some further research work on that. So significant amount of work is still needed from the fundamental research, like we proposed, technology development, hardware prototyping, and the standardization, in order to make this become real and be fully implemented. So that's pretty much our latest publications in this area. So if I couldn't explain all these things clearly, you can refer to this paper. Okay, I know I'm almost running out of time. I would like to take any question for that. Thank you.
Thank you very much. Very interesting talk. We have time for one or two questions.
I just want to ask the relevance, industry relevance of this. You say that the VLC is very much interesting because RF frequency is being scarce. And is there any need from the industry that we have seen, or do you just assume that because RF frequencies are becoming scarce, we want to go VLC?
Okay, the question was whether it's real need for the VLC, even though we know. Well, to be honest, this is a controversial stuff. People are saying that the wireless spectrum is almost out because of the fixed spectrum allocation scheme. Now people are talking about cognitive radio and other things. Thank you so much for this kind introduction. And it's really our great pleasure and honor to be invited here and share our work and also our vision for the future. More or less, I can see the disadvantage of being the presenter after such a good meal with this gorgeous weather. But I will try my best to present our work and try to stimulate the future collaboration. And this is perhaps the second time I got the opportunity to present the work either near the Zoom or inside the Zoom. The first time I did that in Belgium, we have a big skeleton of dinosaurs right in the middle of the hall, and everybody was, I meantime, they're wondering whether they can hold. But this time, we got a very nice, beautiful scene site, and hopefully today I can also share with you the beauty of the integrated network with the power line communication and visible light communication. Can everybody see? If that, I don't need the microphone. Okay, here is the outline of my presentation today. First, we're going to highlight our recent work in the related areas, both for the digital terrestrial broadcasting and also the power line communication and visible light communication areas. And then we're going to provide our proposed, or we're going to share with you the proposed network frame structure of the integrated system of both PLC and VLC. And since this workshop is for the information theory, even though I'm not the guy, the information theory, but I'm trying to show you that how the information theory can help us to achieve our goal. Using one example, basically we propose so-called bit division multiplexing technology. I'm going to give you a bit of flavor on what this looks like and how this thing can help us to improve or achieve a certain system performance. And then I'm going to summarize my talk. Okay, this is the whole picture of my big group. You will see this is not the whole bunch of the group members. In my group, we have 12 faculty members, we have 20+ engineers, and we have over 30 students. And best of all, we also have our future or next generation engineers in the broadcasting area. Basically, as Professor Ferrara just introduced or highlighted, we are the major technical contributor to the Chinese terrestrial television broadcasting standard, which is now the ITU standard. Basically, it deals with the terrestrial digital TV signal over the air. So basically, you don't need the cable, you don't need to use the satellite. So you use either the VHF and VHF, the signal can be automatically delivered to your home, okay? And since we're a big group, we are paying more focus on the physical layer technologies, like from the system level, such as coding, 4-error correction coding, modulation at the receive side, the signalization, channel estimation, equalization, etc. And also we have heavily involved with other standardizations process, such as the broadband power line communication, and also we have proposed the power line and visible light communication integrated system. That is hopefully can be eventually accepted. That proposal can be accepted by our National Standardization Committee. And one of the achievements of this center is we have successfully promoted DTME to be the international standard, ITU standard, power means radio communication. And this one, I actually had the honor to take the photo with our honorary chair of study group 6 of ITU. I would like to invite people in this room, make a guess. How old is this gentleman? How old this gentleman is?
90.
Can I make a very quick poll? How many people say it's in his 70s?
Yeah, about
Okay. How many people say it's in 80s? Great. But it's kind of unfortunate. Neither answer is correct. This gentleman is now 93 years old. And another quick poll is, how many people in this area would be interested in the broadcasting area? No. Great. I see so many young students who love to do that. That one encourages us. If you're in the broadcasting business, you have better chance to live longer. This gentleman is still traveling a lot. He's from Russia. He can still make a 3-day trip from St. Petersburg to Geneva, 3 days. So I'm kind of hoping that in the future we may invite him here. Anyway. Okay, that's just a bit of flavor on what our research lab look like, and then we're going to focus on some research progress in our research lab, which laid down the foundation for our current development for the PLC and VLC related system. Basically, for the traditional orthogonal frequency division multiplexing, which people are familiar with, we use so-called coded OFDM, and also we add certain cyclic prefix in front of each OFDM symbol. With this arrangement, you can mitigate the inter-symbol interference if the channel is dispersive, or you will see the delay spread of the channel. meantime, you will see that with this arrangement, this one is going to help to mitigate the inter-symbol interference. And in the meantime, you also need to insert certain pilot, which means a known data sequence, to train the receiver, such that at the receiver side, the receiver knows what the channel looks like and how to equalize or offset the degradation caused by the channel. So that one caused certain overhead, and including with this CP. I noticed that one of the students in the previous presentation has noticed this loss and also calculate that. But basically, this is the whole arrangement, how this OFDM technology can be effectively utilized for the wireless channel. And this is the whole arrangement of this OFDM symbol arrangement. If this one is the subcarrier index, this one is the time domain, you will have the so-called scattered pilot and continuous pilot to help to synchronize the channel and help to estimate the channel variation. And in our case, we propose another technology. We basically had the so-called PN sequence, which is a known sequence between OFDM symbols. With this PN sequence, we can use this to help to synchronize the channel, and in the meantime, for the channel estimation. With this arrangement, if you compare the parameter between these two technologies, you will see that this technology can help you quickly achieve the channel synchronization and help you to estimate channel in the time domain quickly. But there is no free lunch. Basically, with this arrangement, you actually destroy the orthogonality between the OFDM symbols, or in another word, you actually cause or introduce certain inter-symbol interference. So this inter-symbol interference, if I read that in the time domain, before the dispersing channel, you will see this is well aligned. But after the dispersing channel, something like this, you will see the data, which is the dark black, will disperse it into the PN sequence, while the PN sequence will fade into the data symbol in time domain. So if you want to estimate the channel using the PN sequence, you need to consider the interference from the data. And in the meantime, if you want to recover the data from the OFDM symbol, you need to consider this impact from the PN sequence. So there is mutual interference. Basically, we need to use certain iterative cancellation algorithm to cancel that. The good news is that with this, even though we have to pay a little bit cost for the complexity, but in the meantime, we can successfully remove that after several iterations, maybe 2 or 3. Then the estimation will become more accurate, and in the meantime, the impact of the PN sequence on data will be removed. So the performance degradation due to this arrangement can be minimized. But in the meantime, you pay the cost for the complexity, you save the spectrum efficiency arranged by the CP and pilot. You basically try to shoot 2 birds with a single stone. So this is one technology we have developed. And the second one is we have revisited the bit interleaved coding modulation with iterative decoding and demapping for the better system performance if the channel is non-Gaussian. Usually for the fading channel, traditional coding modulation technology won't be able to provide you satisfactory performance. You need to consider that. A little bit complicated algorithm, but in the meantime, you get significant performance improvement. And this is a very brief history on BICM ID. It was originally proposed something like this. And later on, we are trying to add, based on the traditional bit interleaved coding modulation with iterative decoding demapping, we propose the docking technology and also the signal space diversity. So basically, adding all these together, you pay the price for the complexity. In the meantime, you enjoy the performance improvement. And the good news I would like to report to you is we have successfully incorporated this algorithm into our new next generation standard for the DTTB, and we enjoy really the performance improvement for that. And also for the traditional modulation, we used to use the square constellation mapping like QF. But if we look back for the Shannon formula, we know that if the constellation mapping distribution is more or less Gaussian approaching, you will have better chance to achieve the channel capacity. So in this case, we figure out that APSK is more Gaussian approaching in terms of this distribution than the quant. And in the meantime, if you use gray APSK, you actually can maximize the Euclidean distance to enjoy better performance. So this is another thing we have developed in our lab throughout the whole world in the past 10 years. And now, with that background in the broadcasting, we can somehow leverage what we have learned from that area, try to build up the new system in the new area, which is called the visible light communication. So this is the benefit of having the visible light communication. So basically, I remember one professor from Scotland, Edinburgh University, he mentioned that all over the world there is 14 billion LED lamps. So if each LED lamp can serve as the base station, then basically you're well covered. But you need to understand that each LED is only a single transmitter. You need a source to feed in the information to here. And if you want to have the two-way communication, you need to find another way for the return channel. So basically, we figured out that if we consider the existing infrastructure, and if we want to make these OLED lamps working like a base station, we can somehow use the infrastructure from the power grid or the state grid to send the information such that now we can convert both the illumination and the communication network together with the existing power grid. So here is some